All right, let's start. Hello, everyone. This is Dr. Yuzo. This is ECE 318, Electronic Circuit 1. And today is our 22nd lecture. And can you guys hear me well? And also being able to see. Thank you, Shane. And here we are at this very cell in the Gantt chart. You can see. Obviously, today we have project assigned. Okay, it's actually right after the lecture. Okay, 2:20. The project going to be available from the Canvas. Okay, so please go there to download the instruction to read through. We're gonna go through that instruction together as well during the lecture. Okay. I know we lost one lecture Tuesday. Because of one tragedy, as you know, but we are not going to change the Gantt chart progress plan here. Okay, so everything remains the same. Okay, every due date remains same. The progress remains same as well, which means today should be the very last lecture for the module 5. Okay, I think we are able to make it. Based on the background from MOSFET. It's actually very helpful. Okay. Any questions regarding the course?
I do have.
Yeah, go ahead. Go ahead, Shay.
I do have a question about the lab. Would you be willing to? Yeah. Would you be willing to make some of the labs available before the week that they would normally come out?
Okay, I will do that. I will make that happen. So because we do have one lab report due, and also including lab 11, we have 2 lab reports due, and how many labs? 3 labs. Okay. 3 labs and 2 more lab reports due. So you probably wanna, you will be able to kind of rush to finish all of them and submit the report earlier. That's not a problem. Okay, so I will release all of the instructions. I will do. Okay, will do. Any other questions? Okay, I want to bring up one thing about the lab 11. Like I said, the due date remains same. Okay, we are not delaying by 1 lecture time. No, we are not doing that. Okay, so due date remains same, and also lab 11 shouldn't be a very difficult one. And a bunch of the DC analysis for the Bdt circuit. So no better examples other than the slice examples as well as the lab 11 for you to exercise. DC analysis of the Bdt circuits. So pay enough attention, put enough time on it, and simulate them into the multisim, and then write a report. Okay. If any questions, just shoot me email, or some students prefer to leave a message in the Teams. That's fine too. And this is the labs. And if no further questions, let's step into today's lecture. The first thing about today's lecture is actually the homework 4. Homework 4 has been returned, graded and returned. But just one thing I think I need to bring up. But this is the 4.33 question C. We have discussed in previous lecture. Very good. However, I still see some significant mistake here. First of all, this circuit, you need to figure out clearly, okay? And some students do making mistakes here. You need to figure out why and how, okay? And the second, just looking at this circuit, because in last lecture, I transformed it to this circuit, which is much easier to see the equation. However, if you don't do that conversion of your circuit and keeping this circuit, This obviously is the first version of the circuit you can come up, right? That's absolutely fine. You're not changing the circuit. That's absolutely fine. However, if you're watching this circuit, let me ask you, is this equation correct or not? Everybody take a look. This circuit, is it correct or not? Obviously, this is a KVL inside of this loop, right? Inside of this loop. So here is VGS. So take a look. Is this equation right or wrong? Kevin said looks right. Any agreement or disagreement? Shane agrees with Kevin. Any other answers? Josh agree with those both. Unfortunately, it's wrong. Okay, absolutely wrong. Where's the mistake?
Don't you need RS and RO parallel?
Oh, very good. Why is that, Daniel?
Because they're connected to the source on one end and a ground at the other.
In other words, what happened is you look at this loop, okay, this is a KVL loop. You have VI, VGS, no problem. However, you need a voltage across RS, correct. However, what's the current flow through RS? Is it VGS times the GM? No. A current flow through RS is not equal to GM VGS. Why is that? Because of the existence of R naught here, okay? Your current of this dependent source reaching this node, and then some of them go this way, the rest going through RS. Does it make sense? So the RS current is not equal to the GM VGS. That's why here is not right. Does it make sense? That's pretty much a KCL here. You need to take a look at the circuit, okay? The current of the dependent source, is it completely goes through RS or not? Because it doesn't in this particular case. And how to fix it? How to fix it? Well, this is the problem, exactly the problem of this circuit look. Okay, it's very hard to see from this circuit. This is the major reason why I do a conversion to this way, to this way. From here you can easily tell. Okay, from here you can easily see it. From here you can easily see it. So you're doing a KVL inside of this loop, then you have negative VI plus VGS, right? And then plus the voltage here, right? From source to drain. What is the voltage of here? You have RS and R naught parallel here, right? And the current through them is just equals to total current in this guy. So GM VGS times RS parallel with R naught equals to 0. This is the KVL. From here, I have to admit, from here, it's hard to see. And from here, it's hard to see. But you got to be careful. Okay, you got to be careful. Any questions regarding this? And it's very important, okay. A similar thing you will see in the BJT small signal circuit as well. Okay, similar thing. And also in the BJT, you see this is not open circuit, okay, which makes the things even worse. Okay, this is the one of the problem in the homework. And if this is fine, then we go ahead to try to finalize our DC analysis. Now, first of all, of course, we need to review the DC analysis arsenal. Yeah, arsenal. We have an arsenal here. Always be aware of it. And so, to find the DC results, which means these two guys. Okay. This is DC results, obviously. To find them, you need a circuit first. Right? How to find a DC circuit? This remains same as in MOSFET. Okay? Open capacitors. Rid of the source. Right? And then from this DC circuit, you go ahead to find equations. Right? Here, the DC analysis of Bdt is actually easier than MOSFET, I would say, because the formula, the equation is very easy, isn't it? For emitter current is equal to 1 plus the beta, gain beta, times the base current. Your collector current is equal to the gain times the base current. And also, the nicest one is the VBE. The VBE or VEB is a constant. It's constant. Generally speaking, is 0.7 volts. And or any close value according to the given in the problem. Okay, just be careful to read it. Anyways, VBE is a constant. VBE is a constant voltage value. It's very, very nice and easy equation. You don't want to forget. Okay. Of course, by the way, anyone can tell why VBE or VEB is 0.7 volts. Do you have any memory connecting to something? Why it is 0.7? The 0.7 volts is actually
material.
Is the material 0.7 volts threshold voltage? Threshold of what, Kevin? It's because of the material, correct? Okay. However, the material cannot explain the value, right? I mean, the material silicon is making this 0.7 volts happen. Germanium can give you 0.3 volt. I understand that, but why 0.7 volt? Why not 0.5? Why not 0.9? 0.7, we had this before somewhere. Can you link back to then?
Is it the cut-in voltage?
Of what?
The transistor.
No, we don't have cut-in voltage of transistor. Right. Breakdown voltage? No. You guys are not linking to that. Okay, that's fine. BJT, in terms of the structure, anyone remember it is what? It's actually back-to-back two diodes connected in series. And the VB, or say the base and emitter, is actually one what? One PN junction. PN junction cut-in voltage is 0.7 volt. That's why. Okay. Base and emitter, if you just independently looking at base and emitter, it's actually a PN junction. It's a PN junction. There is nothing but a diode. That's why it's 0.7 volt potential there. This is what I mean by linking to something we have ever learned. Okay. Remember, it's back-to-back two diodes, actually. Two PN junctions. And two PN junctions. It's actually linked to there, a diode, 0.7 volts. It's not a coincidence. It's not coincidence. Okay. And these are three equations. Okay, you don't want to forget. Very, very important. The rest of the thing is actually in similar pattern to the MOSFET. First, you want to find the voltage at not gate anymore, but base. The base. How to find that? You need a KCL. Maybe we'll see the example. Second, you need not VGS loop KVL, you need VBE loop KVL, right? The last top to bottom KVL, okay, including the path of through the VCE. And this is pretty much a similar pattern to MOSFET analysis. So this is DC analysis arsenal, based on which you are going to find a VCE and IC. And the last step of the DC analysis is checking if it is active, to see if it is active in the active region. Okay. Here, if it is, we are done, no problem. But if it is not, in other words, the VCE is lower than the VCE saturation, what are we gonna do here? And this is something new. This is something new. Okay, here is something new. What we're gonna do is just give the VCE value of saturation voltage value. Let VCE equals to saturation voltage value, which is approximately 0.2 volt. And then redo the rest of the circuit analysis to find ID. I'm sorry, IC, right? So this is what we're gonna do, okay? And this is a little bit of review, and we keep going to the example 3. We have done the example 1, 2. In example 3, I still gonna leave 3 or 4 minutes for you guys to do this yourself. Even algebra is very easy, since we don't have quadratic equation, right? So it's not very difficult. So go ahead to find IC and VCE here. First of all, this is what? NPN, right? Can you tell it? This is NPN. Okay. The arrow is from base towards emitter. So this NPN type of Bdt. Okay. You have one identification here you need to conduct. Right? It's NPN, and then go ahead to find IC and VCE. Give you 3 to 4 minutes, and then I will present the solution. And here VBB here, this voltage at this node is given. Okay. Of course, be careful here. This VBB is not what? It's not VB. Okay. These two are different things. VB is here. Okay. This is the base. This concept need to be very clear. Okay. VBB is not equal to VB. Okay. Here, they're not the same node. Right. Carry on. Of course, let me know your answer if you're done here. All right, let's take a look at the solution here. Okay, applying those arsenal weapons. So first we have this equation, right? Now this equation is what equation? VB loop KVL, right? VB loop KVL. We know the voltage at the VBB. That works. Okay. Not necessarily VB itself. Right? VBB works. So inside of it here, VBE loop KVL. Second, we have two, I call them as free equations. Okay, don't forget to use them, right? Free equations in terms of the given beta 75. Of course, back in the first equation here, we already applied the VB equals to 0.7. Okay, we are not wasting it. The last is from a top to bottom pos KVL. From positive 1.8 to negative 1.8. But mathematically, we have four equations. Let's see how many unknowns. IB, E, C, and the VCE. Four unknowns, four equations. Perfect. Anyone received any algebra value based on what you have? That's fine. Anyways, IC equals to 0.2 milliampere. 0.2 milliampere. And the VC is obviously satisfying active region. So done. Now take a look to see any questions, anything. We need to refresh more. Any questions? Everything's good. All right, now we can move on. This is example 3 here. Okay, example 3 here. Example 4. Another 3 to 4 minutes. Go ahead. And we will, of course, for each example, we are learning something new. Okay, it always has something different or say new comparing to the previous examples. Okay, go ahead. All right. Obviously, some of you have already seen the problem of the problem, right? So let's see. I think analysis-wise is okay, right? These are the equations, and we have pretty straightforward current gain equation, the free equation, and this is the BB loop KVL. Yeah, this is from top to bottom KVL. Yeah, no problem. These should be very straightforward. However, what's the problem here? Turn out that VC equals to 3.28. Negative. There's no way for this to be right. Okay, no way for this to be right. But what do you find? Is this conclusion? Okay, it's less than saturation voltage. So this active assumption was wrong. How to deal with it? It means now the Bdt is biased in saturation region. Therefore, the solution is give the VCE 0.2 volt. Okay. And substitute 0.2 volts of VCE back to the analysis, and then you find IC. Okay. What does it mean? It means this circuit is not a amplifier circuit. Instead, is what? Switch on and off circuit. So Bdt works as a switch. Saturation region of the Bdt is what? On state. Remember the IV curve? In other words, this result is telling you that when the Bdt is turned on by this 8 volts, what happened? Bdt is feeding this amount of current to what? To this RC, which could be considered as what? Load. Does it make sense, this circuit now? This is what? This is basically a what? How about I'm saying this is a on and off LED circuit or something similar, right? You have a, or even you have a bulb here or any load. The turn on and turn off, which means this Bdt is a switch. Turn on and off the feeding to the load, right? And how much current it can feed to the load? Here we go, 2.45. Does it make sense? This circuit, it's actually a practical circuit. Okay, how you design a switch, because you have control. Okay, you have control here. Okay? So it's not mechanical, physically flip on and off of the toggle or something like that. Okay, it's electronically controlled switch. Any questions? Everything makes sense so far? Any feedback? Any comments?
Yeah, I'd say everything makes sense.
All right. Thank you, Shay. Thank you, Shay. Yep. All right. If these are fine, then we can move on. Okay, we can move on. What this the example for is, once again, is dealing with the saturation case. Obviously, we can't go any further for the AC small signal analysis. Okay, we can't do that. All right, example 5. Example 5 start to look like what we are used to, right? All right, go ahead. Find IC and VCE. Find IC and VCE. And then there are 5 minutes, 5 or 6 this time. Go ahead. All right, let's see the solution together. See if it works. First, I'm applying a voltage divider at the pretty much the base between R1 and R2, and like I did in the MOSFET circuit. And in the VBE loop KVL, I have this equation. And then the free equation, don't forget to use. And then we have from top to bottom pos KVL here, right? These are the equations. And then I end up with IC of 2.7 milliampere, VCE of 3.51 volts. Let's take a look to see any questions. Everything makes sense?
Yep.
All right. Shane is fine. How about the others?
Yeah, I'm good.
All right, Josh is fine. Daniel is fine too. And everybody be careful. Look carefully, okay? Once again. And once again.
This is like the lab, right?
It's like the lab. What does that mean?
Like it looked like one problem from the lab.
Which lab?
The lab 11, the last problem.
Probably. That's possible. But the key is, obviously, it doesn't matter where you saw this before or not. But the key is, what's the problem? What's the mistake here is making? Can anyone tell?
I kind of recall you mentioning something about not being able to use voltage divider.
Good. Okay. No, I recall that. You're not able to do this voltage divider, okay? You're not allowed to do this. Why is that? Let me explain this better even in the...
Because there's another path for the voltage to take.
Which is the other path you mean?
To the right through the base and emitter.
Exactly. Okay, exactly. Everybody. Okay, everybody, we need to understand the one simple truth like this. Previously, in MOSFET, what we have is you have a power supply on the top and two resistors. Maybe this is ground or another negative power supply. It doesn't matter. You have R1 here, R2 here, right? If here is connected to the gate of the MOSFET. However, remember, this is an open circuit. There's no current here. Of course, you can voltage divider to find a voltage here or here, depending on the ratio. Now the BJT here is not open. Okay, here is not open. You connect to the base. I'm sorry, it's like this. I'm not drawing the BJT. So, right here is not open. You have a current flow here. You have it in the middle. You have in intersection with another path. You doing voltage divider between these two? No, you can't do this. This is wrong. This circuit one knowledge. Does it make sense? This is why. Okay. You can't do this voltage divider. It's not allowed. Then what can you do? Remember, I always said the voltage divider, current divider has constraints. They do have constraints. So they are not working universally valid. But what is the principle or basic knowledge we can use in any scenario? In other words, there's no constraints, always right, no matter what. What is it? As Noah mentioned, KCL or KBL. Okay, they're always right. There's no constraints. Well, of course, as long as you're able to write them correctly, right? If you are making some mistake, that's not a fault of the principle. Okay. The current and the voltage dividers, you need to identify them first. This must be a, what is called single loop, right? Single loop circuit or a single node pair circuit. You are able to apply the voltage and current divider. This is the knowledge back in circuit 1. Okay, so here we can't do that. This is not single loop because of the existence of this path. Okay. And coming back to our shift key is still not working, so I have to do this. So once again, trying to make it very, very impressive. Okay. Wrong. You can't do this. You can't do this. What's the correct solution? Is highlighted by yellow. Highlighted by yellow. We need to do a KCL. KCL. In this KCL, we can read. So first of all, current here equals to what? Current here. Because this is IB, right? This obviously is IB. However, you need to be very clear what's the direction of IB. IB in this NPN BJT is what? Entering the base. Towards right. Okay, once again, the base current IB direction is up to the type of the BJT. Okay. It's towards right. And then this current just equals to base current plus the current downwards through R2, right? That's how we come up with this KCL. And if this is fine, then the rest of the thing remain same, right? Remain same. They are not wrong. They're not wrong. Okay, so eventually the correct IC is 2.16 milliampere and VCE is 4.81 volt. It's big enough to be active. Any questions? Yep, this is the point you need to be very careful. Okay. Of course, here look at the result. Look at the result. Okay, IC correct one is 2.16. Back to the wrong one. What is it? 2.7, right? 2.16 and 2.7. Well, it seems not so very much different, isn't it? Why it is not terribly different? Why is that? Can anyone tell why this wrong answer and right answer are not terribly different? Anyone can tell why? Oh, very good. Okay, Kevin is right because IB is small. IB is small. Okay, even though it is not open circuit, the current flow through the base is small. Okay, this is the objective fact. Okay, it's objective fact. Okay, we can't change that. We can't change that. Okay, IB is small in microampere. Okay, if you end up in your calculation in future, you can check if your IB turn out to be like a 1 milliampere or 2 milliampere. Well, very likely to be wrong. Okay, it's supposed to be in microampere. So IB is very small. IB is very small. Okay. That's why the wrong solution is not ending up with terribly off result. This is the correct solution. This is the correct solution. Okay. Good. Example 6. I think that's the last one. Go ahead. Another 5 minutes. All right. Because of the time, we have to move forward here. So let's see the equation here. At least check with yours. First KVL at the base, we obviously we need it. We need it. The only thing is that we are not able to directly find a VB. Okay, this is one equation including two unknowns. Obviously, we are not able to find a VB from the first equation itself. No, we can't. But don't worry, just the one. This is one of the equation. We have VEB loop KVL. VEB, not VBE. So this is a PNP. Okay, you know this PNP at the first place. You should. Okay, so the VEB loop is up here. Right? It's up here. Okay, this is the up here VEB loop KVL. Two free equations. Never forget. Okay, they remain same and valid for both types of Bdt. Right? And the last from top to bottom pass KVL. Right? And be careful, everything, the subscript of voltage is VEC, not VCE anymore. These are the equations. And as I said, the calculation-wise should be easier than MOSFET since there's no quadratic equation, right? And end up with the IC and VEC. And VEC is obviously big enough. So take a look at the equations and see any questions. All right, if this is fine, we can move on to example 7. So give you guys another 5 minutes to do this. So carry on. All right, let's see the equations and solution. Anyone get any value here? Nothing? All right, then we can see here. These are the equations, right? Just be careful. This is NPN or PNP, by the way? PNP, that's right. Okay, so you're looking for the VEB loop. Give you which is this loop. Okay, which is this loop. Right. And then you have this KVL inside of this loop. And the free equation, once again, don't forget to use. And this path is what? The path is beginning from the positive V plus all the way through VEC down to 95. Okay. Once you got IC and the VEC, well, you know the IC is the current flowing through the transistor. VEC is the voltage, technically the voltage across the transistor. So the product between two is equal to the power of the transistor. Okay. This is so-called the power dissipation. Okay, the power dissipation. VEC or VCE, they are the voltage across the Bdt. IC is nothing but current flowing through it. Okay. Any questions? Anything? All right, if this is fine, then we can move on. We also have a concept of multi-stage Bdt circuit. Okay, just like the same thing in the MOSFET circuit. And actually, this multi-stage Bdt circuit, actually two-stage circuit, are the ones we're going to use in the final project, you will see. And also inevitably including the loading effect. Okay, so the input, this voltage amplifier, one followed by another stage. So the total gain is equals to the output voltage here divided by input here, right? And equals to what? The product between two stages gains. Product, not sum. One of our midterm multiple choice, right? Anyways, and here loading effect you need to worry about, which means you want to make the input impedance as high as possible, make the output impedance as low as possible. Yeah, just this guy here. Loading effect. These concepts remain same as in the MOSFET. And here, we have cascade and cascode once again. Same thing in the MOSFET. So let's identify. We have Q1 and Q2, Q1 and Q2 as well in the second circuit. So in the first circuit, Q1 is what? No, Kevin. The gain of multi-stage here is equals to the product, which means multiplication, rather than sum. Okay, I had a derivation back in the MOSFET. Okay, it's multiplication, okay, product, and not sum. Sum is not right. And back to here. Let's see, Q1 and Q2 respectively are this Q1 is what? NPN or PNP? NPN, right? Q2 is what?
PNP.
PNP. And here's both are NPN. right? Both are NPN. Both are NPN. So let's identify the common circuit, applying the exactly same concept we learned before. So Q1 is common what? Q2 is common what? In the first circuit here. Q1 is what? Q2 is what?
Q1
Same
is
thing
common
here.
emitter.
And the Q1 is common emitter. Q2 is what? Yes, common collector. Okay, it's a common collector. Right. Here, Q1 is common what?
Common emitter.
Emitter again. Okay. Q2 is what? Base. Here we go. Good. Not bad. Not bad. Not bad. All right. If these are all clear, then any questions, by the way? Any questions? Anything need to be repeated? All right. Now we can move on to take a look at the project. Now let's see the project together and roughly go through it and then leave a little bit of time because we can even take some time next Tuesday before the break. We can still talk about the midterm 2. So now let's take a look at the project. Like I said, it should be available in the Canvas in 10 minutes. It's designing an amplifier and designing cascade amplifier. So as I said, 2 stages. The first one is amplifying stage. Second is output stage. 2 stages. Okay. And here is specifying the input signal. Okay. Input signal is specified as 10 millivolts peak voltage, 2 kilohertz AC. A very small AC input. Makes sense. We're expecting to see amplified output, right? The tricky thing is we are adding a load. Okay, so the load very small, 10 ohm. What are you expecting? You should expect to see what? Very hard to have high gain. Why is that? Because your output resistance is so small. According to the voltage divider, the smaller the voltage, the smaller the resistance, the smaller the voltage it is able to occupy, right? So your load is so small. How can this guy occupy a lot of voltage, right? Does it make sense? That's the tricky part. That's exactly why we need output stage to take care of the output resistance. You lower down the output resistance so that you are able to pass down the majority of the amplified voltage here to the load. Does this make sense so far? And since we only have two stages, it's not complicated or completed enough, so the required gain is only between 6 and 10. Okay, with load. Okay, be careful. This is with load gain. Load is 10 ohm. Okay. Somehow you need to design a circuit so that with load the gain is between 6 and 10. Okay. You can try if without load the gain is very high. Okay, the gain is very, very high, over 100 maybe. Okay. However, with load it shrinked a lot. And you only have 9 volts VCC available, and you don't have negative power supply. Okay, you only have 1 positive 9 volts available. And the Bdt is given as this, and And you need some parameters to do the design calculation. So we're assuming the beta gain and thermal voltage, and we are neglecting the output resistance, open circuit. Yeah, resistor are the things, exactly the things you are going to design. Okay, you're going to choose some of them to design the rest. Okay. Obviously, you need to choose some first and then design the others. Some capacitors as coupling capacitors or even bypass capacitors you can apply, feel free. And I provide a roughly a design procedure for you to follow. And basically, you're trying to implementing two Q points for two common emitter circuits. But be very careful, okay? This is a figure 3 cascade CE circuit. This is a one stage. You're seeing cascade 2 CEs, right? However, this is one stage, which is the stage amplification. Okay, this is just a one stage. Second output stage is this common collector circuit. Okay, I'm giving you the circuit. You don't have to design a circuit. You just need to design the resistors. So figure 3 is stage 1, amplification stage. Figure 4 is the output stage. So 2 stages. To stage 1, you have 2 CEs, and I respectively providing the Q point for you to better, easier to design the resistance value. Okay, Q1 is here, and you're designing the Q1 here. Q2 is for Q2 here. So with the provided Q point, I believe is easier for you to design the resistance value. Okay, and also some hint on the resistance values. Like R1 through R4, they should be big. Why they should be big? They are here, here, and here, here. They're pretty much related to the input resistance. Okay, the higher, the better. And RC1, RE1 should be around these two values. And I'm giving you, I'm trying to then narrow down the range design range. And RC to RE2 also, I'm giving you a range to follow. Not range, but around certain value. You can tuning to achieve better gain. RE also again giving you a value approximately to design around. Okay, some hint here. And here I'm providing the lab report rubric. So total, how much points we have? How much point? $20 points, and 20 points, and how much weight the project towards the total final grade? Anyone remember? It's here, right? It's here. It's what project is 17%. 17%. Yeah, 17%. It's roughly kind of a 1 point here is about 1 point in towards your final grade. So it's significant. So it is significant. Okay. And follow the rubric to provide your report. Okay. Assign it today and due by noontime. This is noontime. 12 p.m. is noontime. Okay, it's not the midnight. No, noontime of December 14th. December 14th. That's the very first day of the final week. Okay. There's no uniform standard key. Yes, I'm not saying your resistance has to be certain value. No, I'm not regulating that. Okay. The only requirement here, listen carefully, the only requirement here is here. This is the only requirement. You're implementing this. You're making this happen. Of course, the constraints is these. Okay, you're not using different value of load. You're using 10 kilo ohm load. Well, of course, your gain going to be very nice. However, that's not satisfying the requirement. Okay, your load must be 10 ohm. You must use only 9 volt DC supply. All right. So simulate the design in the multisim and follow the requirement here to write a report. Okay. Any questions regarding this roughly? I think you need to look into it. Start to do it in the middle of the doing. You might have more questions, but is there anything now? All right. We are running out of time here, but we can leave the review of midterm 2 to the next lecture, next Tuesday, right before the Thanksgiving break. But here, I think we can roughly take a look at the where is it? No, here. In the announcement, I have provided the statistics. And here, the grade here, the number here is referred to the total grade of your exam paper, which is out of 45, and your online multiple choice, which is out of 15, right? So the sum of these two is your grade, and then you can find your letter grade level based upon this provided statistics. Average is right up around the 75%. It's a little bit lower than that. And the highest is 57. And the lowest is a little bit more than 50%. And here are the number of students. Yeah, so basically most of you guys did a fairly good job. However, I'm still expecting, well, we have 9 students, 30%, 1/3 of you guys are equal or beyond A minors. Not bad, but it could be better. It could be better. It could be better. There's some basic things still not quite solidly established. For example, the problem, the handwritten works, number 1, the small signal circuit. Well, I won't spend enough time on it to explain, because also very helpful for your very last exam, okay? Because the linkage between the MOSFET module 3 and 4 and module 5 and 6 for BDT are very close, right? If you understand, the better you understand the midterm 2, the better you would do for midterm 3. Okay, this link is there. This link is there. Okay. Any questions regarding the midterm 2? Of course, once again, the knowledge-wise, we're gonna review next Tuesday. Okay, you want to try your very best to attend. Okay, there's some basic things need to be emphasized, and not very solid. Not yet. All right, if all of these are clear, and then let's meet next Tuesday to go over everything there. Thank you for attending today's lecture, and see you guys next Tuesday. All right, thank you. Bye-bye.